Hey, so recently I've started learning OpenGL in C++ in preparation for university, or at least that's what I'm telling myself. I took small steps until I was ready to implement my very own Minecraft-style terrain generator. Cause that's what everyone does these days, right? It all starts with the simplest primitive the GPU was designed to draw, the triangle. So let's go ahead and draw one. Beautiful, ain't she? Now you may wonder, what the heck just happened? Well, thankfully OpenGL lets you draw triangles without much effort. All I had to do is add all the vertices to a buffer on the GPU, and then tell it how to assemble them into triangles. And guess what? We got our triangle. Now, arguably it's kind of boring to look at, so let's enhance our visuals by appending another triangle and thus creating the rectangle. A colored rectangle. And to give it color, that is, any color other than white, I had to write something called a fragment shader. All it does is define the color of every pixel that makes up the triangles based on our code written in OpenGL's very own shading language. Here, I am setting the color to teal by having it be not very red, slightly green, and mostly blue. The scene we want to render is three-dimensional. Our screen, sadly, can only display 2D images. The solution? Projection matrices. Now, I'm not going to talk about matrix multiplication here because I can't be bothered. What I am going to tell you is by multiplying by the right projection matrix, you can take the global 3D coordinates of each vertex and turn them into positions on your 2D monitor. That's right. And okay, fine. I may have partaken in a little voluntary campaign of misinformation here, cause we do actually retain the third coordinate, that is the depth, and it's gonna come in real handy real soon. For now though, just look at that absolutely gorgeous cube I'm able to render now. But wait, what the hell is this? Is that shading? How the hell did that get in there? Some behind the scenes magic, that's how. See, if you're at all computer graphics literate, you'll know that in order to calculate lighting, we'd need surface normals, which would tell us which way each face of the cube is, well, facing. For that, I'd usually have to pass the normals to the shaders along with the positions of the vertices so I can include them in the calculation of our output color. But come on guys, do I sound like some sort of uneducated peasant to you? No. Instead, I am employing a hyper-intellectual only technique called screen space derivatives. Just kidding, it's pretty simple really. Since the GPU doesn't render each pixel individually, but in blocks of 4, I could just measure the change in position between those pixels and extract the normals that way. And all of that essentially for free. In GLSL, the aforementioned shading language OpenGL uses, I take the vertical derivative, aka dfdy, as well as the horizontal derivative, called dfdx, and get their cross product, which just returns a vector that's perpendicular to both dfdx and dfdy. Then I normalize the resulting vector to make sure its length is always 1. I am well aware that this way of calculating normals has lots of downsides when it comes to the visuals, but for Minecraft-style worlds, it's honestly just what the doctor prescribed. By the way, using keyboard and mouse input as well as more matrices, and nope, I still refuse to cover them in more detail, I was able to add some video gamey controls to the camera. Finally being able to move around the scene, oh gosh, it's so liberating. To make our cube look more visually appealing, we can also pass textures to the fragment shader and sample them using so-called texture coordinates, or UVs, which are defined per vertex. But hey, wouldn't you need to add UV values to every vertex and pass them to the... No. Anyway, I made use of something called triplanar mapping. Now, the way this works is you take the faces whose normals are aligned to the global x-axis and apply a texture sampled along the YZ plane of the global coordinates. Then you take the y-aligned faces and sample a texture on the xz plane. And you repeat the same principle for the third axis. And again, a Minecraft world couldn't have been more perfect for this technique. Remember when I was talking about projection matrices and how they facilitate the conversion of 3D global coordinates to 2D screen coordinates? And I said that even after this conversion, we still keep the third coordinate? Ring a bell? No? Man, the attention span nowadays. Regardless, when we render triangles as is, we've, got a slight problem. This. Now, why is this a thing exactly? Well, the rasterizer, the thing that fills in the triangles with pixels, just draws geometry in the order it's laid out in the buffer on the GPU. This means that oftentimes it's gonna draw farther away objects on top of objects closer to the camera. How can you fix this? With this line of code. What does it do? Internally, OpenGL records the z-coordinate, that is the depth coordinate that we kept even after projection, for each pixel into a so-called depth buffer. Think of it as a texture that fills the entire screen and is updated every frame. Before drawing a new triangle, we can tell OpenGL to check whether that new triangle would be behind any geometry that is already on the screen. And if that is the case, it just doesn't draw the triangle. Simple as that. Now we're getting to the juicy stuff. If you've ever, played Minecraft before, you'll have noticed that as you move around the world looking for sheep, as one does, new terrain is loaded in the form of square pieces of land, or ocean. These are called chunks and are 16 by 16 by 384 blocks in volume, at the time of recording that is. This volume, of course, includes not just solid blocks, but blocks of air as well. Chunks are the solution to the storage problem of providing the player with a virtually infinite world. All the game needs to do is load in chunks within the player's render distance and unload chunks outside of that radius as an alternative to storing the entirety of the gargantuan Minecraft world on your hard drive. But that's really only half the story. How is the terrain itself created? Well, I'm glad you asked. Consider a block inside a chunk. It can be one of two types, air or ground. The block also has an X, Y, and Z position. So now we can simplify the question of how to generate terrain down to this. How do we determine whether a given block should be air or ground? A simple approach to this would be to just randomly assign a type to each block. And you know what? In fact, let's do just that. And here it is. See, I speak my mind whenever I can, and let me just go out there and say, ugh, that's disgusting, get this out of my face immediately. As expected, there is not much continuity to this terrain, and it would quite frankly be a pain to try and navigate it. So, let's think about this. We need randomness, right? But it also has to be smooth and gradual. Noise. Perla noise, specifically. Without getting into too much detail, a noise function in the computer graphics sense of the word takes an n-dimensional position as an input and returns a single real number value, or in our case, a float, usually in the -1 to 1 range. And most importantly, this value changes continuously across positions. I can now just declare that, let's say, any block with a value below or equal to 0 is air, and the rest are ground. Now that's what I'm talking about. The best thing about this is that I don't need to save and store any of the chunk data. Instead, I can just generate it on the fly, since all I need to calculate the noise value is the 3D position of a given block. So, now that we've answered the question of which block should be air and which block should be ground, all we need to do is take that data and use it to generate the actual chunk mesh. The algorithm I went for is in a way akin to marching cubes, and if you don't know what that is, just check out the article in the description. Here's my approach in a nutshell. For every block in a given chunk, I look at the blocks to the right of it, behind, and above it. If an adjacent block is of a different type than the current one, I draw the corresponding quad. I do this for each one of the 3 adjacent blocks I check, looping through the entire chunk. Sounds pretty simple in theory, right? Where is everything? Hold on. Well, at least it didn't crash. This is looking better, right? You know what? Let me try something. I mean, it's progress. Still not what I want, though. Okay, guys, okay. We're closer than ever. Just need to fix this little artifact, that's all. I finally got it working. Sorta. At last, we shall marvel at the greatness of our creation. Yet, I can't help but notice that it just looks, well, off. What I mean by that is, it looks like Minecraft from, like, 2011. And, well, what was Minecraft missing in 2011? That's right, ambient occlusion. Ambient occlusion is a lighting phenomenon which causes all the corners and like little crevices of an environment to be darker than the flat areas, just simply because of the fact that less light reaches them. There are several ways to simulate ambient occlusion, with fancy names such as ray trace ambient occlusion or screen space ambient occlusion, but guess what? I'm gonna be using neither of those, because so is Minecraft. I'm just gonna check how many adjacent faces each corner has, and write that value to each vertex as a separate attribute. And the fragment shader, I just have to blend between the block's texture and the color black based on that value. The way I've set it up, I can just multiply the color of the block by the R component of the vertex color, since that's where I'm storing the ambient occlusion. And just like that, our world looks a whole lot nicer now. The last thing I had to add to mimic the authentic Minecraft experience is an infinite world. Now, this task may sound intimidating, but we already have the foundation. Noise-based terrain generation, splitting the terrain into chunks, generating the mesh. All that's left is adding chunks as they enter the player's render radius when the player moves around. What I've also done is move the chunk rendering code to a separate thread on a CPU so the whole game wouldn't just freeze when new chunks had to load. And here you go. As you can see, once a chunk is loaded, it just sort of stays there forever, so I still gotta work on that, but that's what I got so far, which is honestly still not enough for me to even consider making it a public repository on GitHub. Yeah, I think I'm gonna call it a day here. Hope you enjoyed this one. God bless.